Hi everyone. Can you hear me well? Can you see my screen? All right.
Yes,
Yeah.
go on.
So thanks for the introduction, Robin. And on behalf of the organizing committee, I would like to also thank all the previous speakers for their excellent presentations so far. So in my talk today, I would like to discuss the mathematics about a new class of transport-based methods using ensembles to solve Bayesian inverse problems and applying these methods to the problem of estimating uncertain model parameters. And this will be a joint effort with my collaborator, Derek Posselt from NASA JPL. And so as you'd see in a bit, these methods are a generalization of the Kalman filter, which I hope most of you would be familiar with. This is essentially a method to estimate the filtering distributions for linear systems with Gaussian errors. And you can see here in the upper right that in this case, the problem simplifies to forecasting and updating the means and the covariances of the underlying state distributions at each observation time. But of course, the limitation of this method is for any other systems with nonlinear dynamics and nonlinear non-Gaussian errors, we will run into biases and errors. So now the question is, how can we overcome some of these limitations? One principled approach for that is to use the framework of measure transport. This is a nice schematic that recently came out of a tutorial by Max Ramgraba, where it illustrates the computational effort involved in measure transport, which is to find a transport map S, which couples together these two distributions, a reference and a target. And once we have the transport map, it's really nice as we can sample from the reference Gaussian here, and we can push forward these samples to sample from the more complex target. And so it really represents a convenient way to generalize the Kalman filter assumptions of Gaussianity. Right, and so our interest in measure transport has been fueled by its rapidly growing popularity, and in particular in the generative AI community. Here in the upper right, for example, you see that it is really the building block for generative models like normalizing flows, where we have a series of transformations that are composed with each other in order to sample from a more complex target distribution. And more recently, there has been a shift in the community toward these continuous approaches that Peter Jan hinted at earlier on, where instead of representing the transport map explicitly, they represent the transport in an implicit way, for example, through the integration of a velocity field in a neural ODE, which gives you the transport in the continuous framework. And examples of those approaches are some of the recent progress in flow matching techniques for continuous normalizing flows, as well as the score-based probability flow ODE approaches that I have taken an example here. All right, regardless of the representation of the transport though, what we want to do is to somehow use these ideas to extend the Kalman filter. And this was done in a recent paper that came last year, where I used transport maps to generalize beyond the Gaussian assumptions of the Kalman filter. You see that in the upper right here that in addition to estimating the means and the covariances of the reference Gaussian distributions, here we need to additionally estimate parameters of the transport map that we use at each observation time. So this is a general picture. The Kalman filter here emerges as a special case of this more general theory, and I'll talk a little bit about that later on. And one of the interesting features that will become important is that at each observation time, you notice that under this new theory, the prior and the posterior, after data is being assimilated, have similar shapes, which is because the prior and the posterior are pushed forward by the same transport map. This is known as conjugate Bayesian inference and has been inspiration for many similar filters, including the quantile conserving methods that Molly talked about, but also gamma inverse gamma ensemble Kalman filters of Craig Bishop. We'll talk about this a little bit in detail later on. The problem I would like to address here as a sort of application of these new approaches is using the new conjugate transform filtering approach to estimate unknown parameters from data. This is a pretty standard problem in the Earth system community where we need to somehow represent these subgrid scale processes using observations, for example, from satellite data. And the way that I'm going to solve this problem here is use the Bayesian framework, where the goal would be to sample from the posterior of our unknown parameters u, given observations y, under the standard observation model that we have our nonlinear model G, which is a map between the parameters to the observations and having an additive Gaussian noise added to them. Right, so two contrasting ways to solve this problem, really. The golden standard is the MCMC, Markov-Chain Monte Carlo, which we know can sample from the correct posterior, but it's simply too expensive to implement in practice, requiring many iterations of the nonlinear model, G, which if this is a climate model, you can imagine that this becomes simply intractable. Another approach here that resolves this issue of scalability is a type of an iterative ensemble common filter that has become known as the ensemble common inversion method. And it really provides gains in computational scalability, but we have to contend with the Gaussian assumptions. So in this work, we would like to address this optimality gap by formulating methods using measured transport and really creating an ensemble equivalent of the conjugate transport theory that I introduced earlier for handling nonlinear models. We will apply this to a single column cloud model as the first implementation and study the impact of different transport maps. So before I talk about the mathematics of these new methods, it is appropriate to also consider the original ECTI paper that was formally introduced by Iglesias back in 2013. One of the key contributions of this paper was to turn the static data model into a state space dynamical model, where the dynamical operator is acting on an extended state comprising of the parameters u and their image under the nonlinear model G. This is a well-known trick in state estimation, essentially allowing us to represent the observation operator as a trivial linear operator. And a more crucial point here is with this contribution in this paper, what it allowed is to use any state estimation technique in order to generate samples from the posterior at each step in algorithmic time, denoted here by the index n. So this is not real time in the case of static problems, right? This is some algorithmic time that the system evolves through. So this is the ECTI formulation. One thing that wasn't mentioned in the original paper, and I think it's an important consideration, is the underlying distributional assumptions used to derive the ECTI update at each step n, which is our well-known Gaussian assumptions over the prior in this first bullet point here, and also over the likelihood. Under these assumptions, we know that the posterior is a Gaussian distribution and its parameters are given by the common filter equations. And this connection to the underlying distributions is quite important as it allows us to think how we can use measured transport in order to generalize the ECTI framework. So now this is what we can do at the level of distributions at a particular time in our iterative algorithm. We can assume that the prior is given by some push forward of a transport map T with some reference Gaussian density. And similar for the likelihood, we have a push forward of another transport map with reference Gaussian density. And we're going to make a further simplification in our assumptions that the transport map over state space can be represented in this block structure, where we have separate components over the parameters u and over the predicted measurements g. And the reason why we make this simplification is that we can recover the linear observation operator used by ECTI algorithms. Now, using some of the theoretical results from my 2025 paper, we can show that under these distributional assumptions over the prior and the likelihood, the posterior is available in closed form. We can write it exactly and analytically. And you can notice here that the transport map appearing in the solution is the same transport map that we use for the prior, but the reference Gaussian parameters are updated using the common filter equations. In the special case where all the transports are identity, we recover the standard common filter. And in nonlinear cases, we still preserve the common filter structure in the latent space, which is important as it allows us to use efficient ECTI methods to update these latent parameters. As I said, we will be testing some of these ideas for a application of a idealized cloud model where we'll be simulating the evolution of a mesoscale convective system. And the goal will be to estimate microphysical parameters from observations. If you're interested in the details of the model, this is the reference here of Derek's paper from 2010, which is this idealized model is essentially the microphysical code from NASA's Goddard's atmospheric prediction system. In our experiments, we will consider two configurations. In both of these configurations, we have two observations of long wave and short wave radiation, and they differ by what we try to estimate. So here on the left, we have the densities of graupel and snow particles, and on the right, we have the fall speed parameters related to graupel particles. The reason why we're interested in these two configurations is that they share different complexity in the Bayesian posterior. Experiment A is much simpler in terms of the posterior structure, whereas experiment B has this really complicated bimodal posterior structure, so much harder to solve using standard methods. For each one of these experimental configurations, we'll be configuring it with 30 different values of the true parameters, and we'll be averaging our ensemble results over 20 random trials. So as a first study, here we're really interested in a non-iterative version of the new Ensemble Conjugate Transform algorithms, which means that we only require to run the forward model G one time, as opposed to 10 to the 4, which may be required by MCMC. And we have really are interested in studying the impact of different transports. We have 15 configurations in total, which can be divided according to the observation transforms and the parameter transforms. On the left, we have the reference configuration with Gaussian assumptions. And then in 2 and 3, we have two configurations with learnable transport maps, which are parameterized using rational spline functions, either component-wise for each marginal or in a multivariate fashion using coupling layers in a normalizing flow architecture. For the parameter transforms, the picture is similar, but here we have these additional fixed transform experiments where we use transforms attempted in previous studies, like Gaussian anamorphosis on one hand, but also bound-preserving transform. The difference between 4 and 5 and 2 and 3 is that in 2 and 3, we don't need to learn any parameters of the transport, so the problem has a similar computational complexity to the ECTI. So some results from experiment A. In the upper left, we have the ensemble common inversion, which is our reference method. These are the posterior results with respect to the Jensen-Shannon divergence. And we see here that for the 30 parameters, the weakest performance of the ECTI occurs for parameter pairs which are close to the bounds of these parameters, which, as Molly already talked about, this is expected due to the non-Gaussian distributions that arise in these problems. For all of the other configurations, we actually have uniform improvements for any choice of the transport map. But for this case, the best improvements are if we use a Gaussian assumption in observation space, and over parameter space, we deal with fixed transport transforms, the Gaussian anamorphosis and the bound-preserving transform, which is expected due to the simpler nature of this problem. By contrast, if we look at experiment B, there is an obvious advantage of using learnable maps in observation space, but the much less intuitive result is that in parameter space, we obtain the best results if we have a Gaussian assumption in parameter space, right? Which is this experiment here in the upper left. So this is a bit surprising because of the non-Gaussian structure of the prior and the posterior, which brings the question, why is this the case? So let's try to uncover this problem a little bit. Here in this slide, I'm plotting the observation space performance of the ECTI as compared to the MCMC true posterior. And we can see that if we use multivariate learnable transport maps, we have an excellent agreement between ECTI and MCMC for both of the experiments. And we do that by only running the forward model once, as opposed to the multiple iterations we require for MCMC. But what this also means is that the difficulty of ECTI arises really as to how this observation space update is mapped to parameter space. And to further understand the source of errors here, we can revisit the structure of experiment B. You see that experiment B is highly non-conjugate. What do I mean by that? The prior is uniform, but the posterior is this bimodal, highly correlated distribution, which violates the assumptions of the new theory, right? It turns out that using Gaussian assumptions or an identity map in parameter space makes the least structural assumptions and allows us to prevent overfitting the prior in solving this Bayesian problem. It's interesting to know that this is a specific feature of static estimation problems and is very different from the type of dynamical data simulation problems that you see here on the right, where this is an example from John Potter-Joy's 22 paper. You can see that the prior and the posterior are much closer to being conjugate as they describe a similar relationship. And this is because of the physical laws that occur in the dynamical problems. Now, the question is, how can we resolve this issue? Remember that earlier on, I made an assumption that the transport map is acting separately over the parameter Cu and the predicted observation G, which we can resolve this issue, right, if we can somehow learn the joint distribution over U and G. The joint distribution can be written as the product of the marginal over G multiplying the conditional of U given G. And I'm going to make now the following approximations. For the marginal over G, I'm going to use the same approximation as I did in the one-step ECTI. But for the conditional distribution of U given G, I'm going to use this conditional map, which, as you can see here in the bracket, it has the additional input of the predicted observation G, pushing forward, again, some standard Gaussian distribution. And what I'm going to do here is to learn the transport maps jointly, simultaneously, from samples of the prior ensemble, which is this pair of parameters and evaluations of the forward model. Now, as Molly nicely led to this theory, there is a two-step formulation of the Bayesian update that we're going to utilize here. I can write the posterior using this integral identity that was described in Groom's 2022. And now I'm going to do a two-step update, where in step one, I'm going to sample from the observation space posterior using the marginal transport map over the observed over G. And then for step two, I'm going to plug in the samples back into the conditional transport map in order to get a sample from the desired posterior. Now, going back to this more challenging experiment B, we see that we have a row of 3 experiments. All of these experiments use multivariate splines in order to parameterize the marginal transport over G. But here we're increasing the complexity of the conditional map, starting from identity, which corresponds to exactly the type of linear regression that is used in DART filters, for example. We have learnable component-wise splines, and we have multivariate splines. So now we see here that unlike the one-step formulation, increasing the complexity of the conditional transport map from left to right leads to increasingly better performance, with the best configuration being multivariate splines for both the marginal and the conditional, and this is much better than the best performing one-step ECTI approach. We can visually confirm these improvements by plotting the performance of ECTI for one of the particularly challenging cases for ECTI, where we see that there is a big difference between the posterior sample and the true Bayesian posterior that has been computed numerically for these experiments. And we see that as we increase the complexity of the conditional transport map, we improve the location bias on one hand, we improve the nonlinear relationship between AG and BG, and lastly, we also improve the error in the posterior variance, okay? And this is the result from the best performing one-step ECTI. So I think in the interest of time, I would stop here. I'll let you skim through these conclusions. and I'll be happy to take any questions. And you're also welcome to scan this QR code, which has a reference to my exact nonlinear state estimation paper, which is serving as a basis for the methods I described here. Thank you very much for your attention.
Thank you, Hristo. Excellent talk as always. We have some questions in the Yopad relating to the transport maps. So Shay Gilpin is asking how much the parameters of the transport maps change between cycles and additionally over the full experiment. And related to Shay's question, I'm wondering if you could comment on the efficiency of learning those parameters, especially if you have to do so repeatedly across iterations.
Yeah, thanks for the questions. Shay, in this case, since we're interested in the non-iterative formulation of these methods, we only have to be concerned with one forward run of the model G. So we only need to estimate them once. And this allows us to sort of have more complexity over the transport map if needed, like in these multivariate experiments. In terms of the computational effort, it's much less the MCMC. If I have to give you some numbers, perhaps for this two parameter experiment using the same compute architecture, MCMC may take something like 1.5 hours as opposed to just a few minutes with these transport-based approaches. And you saw from the observation space diagnostics together with the parameter space that we have a much closer resemblance to what an MCMC would give us at a much cheaper cost.
Thank you, Hristo. If there are no other questions, then with that, I'd like to thank Hristo and